Hello everyone, welcome back. We've concluded our discussion on differential equations the last time. Today we're going to start chapter 7, which is three-dimensional coordinates. You've all seen a three-dimensional coordinate system, essentially just three axes, x, y, and z. So let's start with a quick recap. Here is a typical 3D coordinate system. Okay. This is the x-axis, this is the y-axis, and the vertical one is the z-axis. Let's start with a quick recap, a couple of definitions. First, what's the xy plane? Well, the xy plane, or equivalently the plane that can be described by z equals 0, is, well, it's the horizontal plane. So it's the plane that's this. Right, like I said, it's characterized by z equals 0. So let me just label that here. This is xy plane. Okay, and similarly, xz plane is characterized by y equals 0. I'm not going to draw that again, but you get the idea. So it's the plane that's spanned by the x-axis and the z-axis, and y equals 0. And the last one, yz plane, is characterized by x equals 0. Okay, a typical 3D coordinate is something that looks like this. A tuple with three numbers, x, y, and z. And here this x is the distance from the point xyz to the yz plane. Okay, and the y coordinate is, well, the same thing. It's the distance to the xz plane, and then the z coordinate is the distance from the point to the xy plane. Alright, so this is some basic definition of the 3D coordinate system. Let's try to plot a couple points. Let's plot 2 minus 3 minus 3, and then 1, 4, 0. Again, let's draw the three axes. This is y, this is x, this is z, x, y. Okay, 2 minus 3 minus 3, so it means it's 2 in the x direction, and this is the positive y direction, so we want to go to the negative side and draw 3. So that's negative 3, and we draw a parallelogram using these two numbers, and this is 2 minus 3, 0. To get 2 minus 3, minus 3, you just go down by 3. Okay, actually my example on the notebook is actually, never mind, let's just do 2 minus 30 minus 3. So you get, this is 2 minus 30, 0. To get 2 minus 3 minus 3, you just go down by a distance of 3. And this is our 2 minus 3 minus 3. Okay, you can start from another direction. For example, you can start in any direction you like. For example, you can do 2 and then -3 first in the z direction, and you draw a parallelogram like this. And then since the y coordinate is -3, you go to the left by 3. You'll end up at the same point. So I'm just saying that there are multiple ways to draw this. You just pick a plane, either xy or yz or xz plane. You draw the point using 2 coordinates on that plane, and then you use the third coordinate to get the 3D coordinate. Okay. All right, let's try another one. Again, y, z, x. Well, since now we see the z coordinate is 0, that means it's lying on the xy plane, right? So we no longer need to worry about the z-axis here. We just draw the x coordinate and y coordinate and use the parallelogram to get the plot. So on x, the value is 1, and on y it's 4. So we draw 4 on the y-axis and draw a parallelogram. Not the best graph I've made, but you get the idea. And this is 140. Okay, so this is the plot. This is how you plot 3D points. Let's move on. Next, let's talk about the distance and midpoint between 2 points. So suppose we have 2 points x1, y1, z1, and then x2, y2, z2. Then the distance between these 2 points is given by the square root of x1 minus x2 squared plus y1 minus y2 squared plus z1 minus z2. Oops. If you haven't seen this, you must have seen the 2D version, which is just suppose we're in a two-dimensional space. Then we don't have the z coordinates, just x1, y1, x2, y2. Then the distance is square root of x1 minus x2 squared plus y1 minus y2 squared. So we don't have this part. So this is just like a 3D version of that. Okay. And then the midpoint. Not midpoints, it's just midpoint, is given by x1 plus x2 over 2. So x1 plus x2 over 2 is the average of the x coordinates of the 2 points, and the y value of the midpoint is the average of the y coordinates of the 2 points, and so on and so forth. So we get y1 plus y2 over 2 and z1 plus z2 over 2. Okay, a quick example. Suppose we have 2 points. One, 0, 2. and then 2, 4, minus 3. Then the distance, or usually we denote distance by d. The distance d equals square root of 1 minus 2 squared plus 0 minus 4 squared plus 2 minus 3, so it's 2 plus 3 squared. Okay, so we get square root of minus 1 squared is 1, and then this is minus 4 squared, that's 16, and that's 25. Add them up, you get 42, so it's just square root of 42. And the midpoint we don't have a canonical letter for midpoint. Maybe M if you want to use it. Either way, I'm just going to write it this way. The midpoint has coordinate 1 plus 2 over 2, and then 0 plus 4 over 2, and then 2 minus 3 over 2, which is 3 over 2, then 4 over 2 is 2, and then minus 1 over 2. Okay, so that's the midpoint of the 2 points. Now that we have the formula of distance, we can derive the equation of a sphere. Now, let's look at this diagram. Suppose we have a sphere with center at the coordinate HKL and radius r. What is the equation that describes this sphere? Essentially, the sphere is just all points, the collection of all points that are distance r from the center HKL, right? Therefore, we have this definition: a sphere with center at the point HKL and radius r is the set of all points x, y, z such that, when I write s dot t dot, it means such that. Such that, well, as I said, the point on the sphere is characterized by distance r away from the center HKL. So what's the distance from this point to the center? It is square root of x minus h squared plus y minus k squared plus z minus l squared, and the distance being r. Okay, so this is the definition of a sphere, or this is the equation for a sphere, or we can square both sides because it just seems simpler without a square root, right? So we can square both sides and get the new equation, which is x minus h squared plus y minus k squared plus z minus l squared equals r squared. Okay? And this equation This is the standard equation of a sphere. Okay. For example, what is the equation? What is the equation of a sphere with center 2, 4, 3, and radius r, equals 3. Okay. An equation with center this and radius r can be described by the equation or we just apply this formula directly, right? So our h is 2, k is 4, l is 3, and r is 3, so we have x minus 2 squared plus y minus 4 squared plus z minus 3 squared equals 3 squared, which is 9. Okay? All right. Now, what if you're given what if you're given the coordinates of a couple points and you're asked to determine the equation of the sphere? Well, from the definition or from the standard equation of the sphere, we know that the equation is determined by center and radius. Now, if you are given 3 points, well, then you can find the center and the radius, right? So if you have three points determines the sphere. If you have 3 points that lie on the sphere, you simply find the center by equating the distance, equating the distances from the center to all 3 points. If you find the center, you find the radius. Now, suppose you're only given 2 points. Now, 2 points do not determine a sphere. You can find all kinds of spheres that have these 2 points on it. But a special example is if you have 2 points as endpoints of a diameter of the sphere, then that determines the sphere. Okay? A sphere so for some reason the writing pad is not working very well. All right, it can be determined by 2 points by 2 endpoints of a diameter. I should write this. Well, this is pretty straightforward because if you are given 2 arbitrary points, not necessarily endpoints of a diameter, and you connect these points to form a straight line, that line has no relationship with the center, right? You cannot tell what the center is just by looking at that straight line. But if these 2 points are endpoints of a diameter, then if you connect them, that's a diameter of the if you connect these points, then that line is the diameter of the sphere, and the center lies in the middle of the diameter, right? So we can determine the center from these two endpoints. If you have the center, you have the radius. Okay, so let's try this. Suppose a sphere has these 2 points, 3, -2, 6, and -1, 4, 2, as endpoints of a diameter. Okay, then the center is just the midpoint of this diameter, right? So it's given by 3 minus 1 over 2, and then -2 plus 4 over 2, and then 6 plus 2 over 2, which is, this is 1, this is again 1, this is 4. Now if you have the center, you can calculate the radius by computing the distance from the center to any one of these points. You can choose anyone, whichever one you like, and you'll get the same answer. Okay, so the radius, I'm just going to write r, equals the distance from the center to, let's pick the first point. And the formula of that is 3 minus 1 squared plus -2 minus 1 squared plus 6 minus 4 squared. Okay, and 2 squared, that's 4, minus 3 squared, that's 9, and then another 2 squared, that's 4. So you get square root of 17. And if we now that you have the center and the radius, we can write out the equation for the sphere. Equation for a sphere is x minus 1 squared. Remember that we're using the standard form, so it's x minus 1 squared plus y minus 1 squared plus z minus 4 squared equals r squared. Okay, so it's this equals 17. All right, let me add another page here. Okay, so this example was finding the equation of the sphere from two endpoints. Now let's try another example, another practice problem. But this time, let's try to find the center and radius from the equation. So we are finding the center and radius from the equation of the sphere. Okay, now suppose a sphere is described by this equation, x squared plus y squared plus z squared minus 2x plus 4y, oops, minus 6z plus 8 equals 0. Oh, that's a very bad z. Plus 8 equals 0. We're given this equation, we want to find the center and radius of the sphere. Now, if we have the standard form of of a sphere, then center and radius can be immediately deduced, but just by looking at the equation. The only problem is the equation we're given is not the standard form of a sphere, so we only need to turn this into the standard form. How do we do that? We need to change the left-hand side into complete squares. Okay, so let's group things that depend on x. So we have x squared minus 2x. Okay, and then y squared plus 4y. And then plus z squared minus 6z. Now let's first write out the formula for complete squared. So if we remember that a plus b squared equals a squared plus 2ab plus b squared. Okay, then immediately in this case, if we have, for example, x plus a squared, then we have then this equals x squared plus 2ax plus a squared. Okay, I'm just changing the letters here because we're using x plus something, y plus something, z plus something. Okay, now if we want to form a complete square right here, that means our 2a has to be minus 2, therefore a has to be minus 1, therefore we will get x minus 1 squared, and the constant we need is plus 1. Okay, same story. If you want to form a complete square with y squared plus 4y, it has to be y plus 2 squared, so you need plus 4 here. Similarly here, it has to be z minus 3 squared, therefore you need plus 9. Okay, so now we've added all these extra constants into the equation. We need to subtract them, right? So let's subtract 1 minus 4 minus 9. And then, so far we've taken care of these 6 terms, and then the equation is plus 8 equals 0. So that's the rest of the equation. This is not the best writing, so this is at the end of the equation. Okay, you guys get the idea. Okay, all right. So the complete squares is x minus 1 squared plus y plus 2 squared plus z minus 3 squared. And this is just simple calculation. This is minus 14 plus 6, so you get minus 6. And if you add 6 to both sides, you get equals positive 6. Okay, and positive 6 is square root of 6 squared, right? So let's just write this, square root of 6 squared. And you have the center is 1, minus 2, 3. And the radius . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . is square root of 6. Oh. Alright, so this is how we find the center of radius from the equation of a sphere. Next, let's look at traces of a surface. Well, in particular, traces of a sphere. Let me first define what a trace is. So a trace of a surface is the intersection of the surface with any of the three coordinate system, three coordinate plane. Okay, just right. Okay, the three coordinate planes are, remember we talked about that at the beginning, they are the xy plane, xz plane, yz plane. So essentially we are interested in, it's like a curve on this surface we're looking at that has either 0x coordinate or 0y coordinate or 0z coordinate. Let's see an example. Let's find the trace of the sphere x minus, write that in there, x minus 3 squared plus y minus, oops, y minus 2 squared plus z plus 4 squared equals 5 squared on, let's say, the xy plane. Okay, so imagine you're cutting the sphere with the xy plane and see what that intersection is. First of all, without even solving the problem, without writing anything down, you should be able to tell that the trace is a circle. Why? Because if you have a sphere or a ball and you cut it with a with a knife, and the cross section must be a sphere, right? So the xy plane is like cutting the sphere in the xy plane direction. You should expect the result being a circle. Now let's prove that. Well, if a point is on the sphere, it has to satisfy this equation. And if a point is on the xy plane, then it satisfies z equals 0. So every point on this trace satisfies x minus 3 squared plus y minus 2 squared plus z plus 4 squared equals 5 squared. And then the second equation, z equals 0, because xy plane is characterized by z equals 0. Alright, so every point on this trace satisfies these two equations. Now let's plug z equals 0 into the first equation. We get x minus 3 squared plus y minus 2 squared plus 0 plus 4 squared equals 5 squared. Right? Now 0 plus 4 squared is 16, and 5 squared is 25. 25 subtract 16, you get 9. So you get x minus 3 squared plus y minus 2 squared equals 9. Right? And since 9 is 3 squared, then we know the trace is a circle with center. One more example on the traces. Let's look at the trace of a non-sphere surface. Suppose we have the surface x squared minus 4y plus z squared equals 0. And let's again look at the trace on the xy plane. Again, on the xy plane is characterized by z equals 0, therefore we get x squared minus 4y equals 0. And then we get y equals x squared over 4, which means the trace on the xy plane is a parabola. Okay, that is all for the traces. Let's move on. The next thing we are going to study is planes. So for planes, instead of let me first give you the general equation for a plane. So the general equation is ax plus by plus cz equals d, where a, b, c, d are arbitrary real numbers. Now, let me give you a quick derivation of the formula, but it involves some linear algebra. For those of you who have not taken linear algebra before, if you're interested, you can certainly look into it yourself. It's not a huge deal if you don't know what dot product or inner product is. But anyways, let me just show you quickly how this is derived. For any plane, usually, just think about a plane right here. Okay. How do we characterize a plane? In fact, we only need two things. First, we need a point that is on this plane, and second, we need a vector that is perpendicular to the plane. So imagine that we are living in three-dimensional space. Okay, we have a plane, And so to describe that plane, all we need is a point on that plane and then a vector sticking out of it at that point. Okay, now suppose this vector, let's call this vector, A is not a good letter since, yep, let's call this vector V. Okay, and suppose this V is written as ABC. That's the value of V. And suppose this point P, which is this point right here, is given by, say, what's the letter that would, HKL. Okay, these are just arbitrary numbers, or you can take 0, 0, 0 to make things simpler. Now, every point on this plane, suppose we have another point that is an arbitrary point on this plane. Let's just call that x, y, z. And if you connect this, then this vector, let's call that u, is u is, I know I'm using sharp parentheses and normal parentheses. They mean the same thing. U would be x minus h. Why am I writing here? Sorry. Let me write this in the middle. So it's easier to see. Our V is ABC. And our point P, which is this point, let me write here. Point P, say that's HKL. Then our vector U is x minus h, y minus k, z minus l. Okay, and as I said, the vector v is a vector that's sticking out of the plane. It's perpendicular to the plane. Now, what does it mean when we say perpendicular to a plane? What we actually mean is it's perpendicular to any vector that lies on this plane. So v is perpendicular to u. Now, if you've taken linear algebra, you would know that if two vectors are perpendicular to each other, the inner product is 0. So we have u dot v equals 0. The dot product is a times x minus h plus b times that. So you get a times x minus h plus b times y minus k plus c times z minus l equals 0. Okay, so that's the dot product of u and v. Now distribute all the multiplications, you get ax, well, minus ah. I'm going to move that to the right, so we get ax plus by plus cz equals ah plus bk plus cl. Alright, now this is the d part in our general equation, so let's just call that d, because since HKL is arbitrary, you know, AH plus BK plus CL is arbitrary. So we get the general equation AX plus BY plus CZ equals D. So that's where the general equation for a plane comes from. Now, if you've, like I said, if you've never taken linear algebra before, don't worry too much about it. But if you're interested, I think it's a good idea that to know where these equations come from. The dot product is essentially coordinate-wise multiplication and summation. So the dot product of two vectors is the first coordinate times the first coordinate plus the second coordinate times the second coordinate plus the third coordinate times the third coordinate. And there's a very important theorem in linear algebra that is if two vectors are perpendicular to each other, then the dot product is 0. So this is what I meant in mathematical language. This means u is perpendicular to v, and from that we get the dot product equals 0. Okay. Now we have the general formula of a plane. Let me give you a couple examples, and let's try to sketch these planes. All right, let's try to sketch the plane. Uh, 3x plus 2y plus 4z. When you study a new surface, a different surface that you're not familiar with, it's always a good idea to see how these surfaces can be graphed. All right, how do we sketch this thing? The way we do it is we know that 2 points determine a line, 3 points determine a surface. So all we need are 3 points that are on the surface. Of course, you can choose arbitrary any 3 points you like, but I mean, just by looking at it, it's much simpler that if we choose a point that's on the x-axis, and then we choose a point that's on the y-axis, and then we choose a point on the z-axis, right? Oh, why is this 0? I meant 12. Okay, so those 3 points we choose are going to be the intersection with the x-axis, and then the intersection with the y-axis, and then the intersection with the z-axis. So let's see what these points are. So first, let's consider intersection with x-axis. Well, the intersection with the x-axis means y and z are both 0. So we get 3x equals 12. So that means x equals 4. So this point is 4, 0, 0. Okay. Alright, so this is the point at which the surface intersects the x-axis, and then the intersection with y-axis same story, except that now we have x equals z equals 0, and therefore 2y equals 12, y equals 6. So the coordinate of this point is 0, 6, 0. Alright, at last we have intersection with z-axis. We said x equals y equals 0, then we have 4z equals 12, z equals 3, so 0, 0, 3. Okay, now we have these 3 points on the surface. Let's try to plot this. Here I'm not going to draw the negative parts of the axes, just because too many lines on a graph, it makes messy. So let's just draw the positive parts. So what I mean is this is y-axis. This is z-axis. This is x-axis. Alright, so the intersection on x-axis is 4. So we between this point and then 0, 6, 0, so a little bit longer. Somewhere around here, and then 0, 0, 3. Okay, and to make it 3D, let's connect all of them. And this is the surface we're looking for. Alright, let's try another example. Well, this time we don't really have 3 intersections. Remember, in this case, we chose the intersections with the 3 axes to be the 3 points on the surface. But what if it doesn't intersect with one of them? So here's an example where the surface does not intersect with the z-axis. So say we have x plus y equals 2. Well, once again, you can choose 3 arbitrary points. For example, 1, 1, 1, 1, 0, and then 1, 0, 1, 0, 1, 1, and just connect them to make a plane. But a more intuitive way to do it would be, since z is not involved in this plane equation, we know that the surface must be parallel to the z-axis. So we only look for the intersection with the x-axis and y-axis, and then we just draw a surface that connects these 2 points and also parallel to the z-axis. So what I mean is this. We find the intersection on x-axis and y-axis. Obviously, it's going to be 2, 0, 0, and 0, 2, 0. So these are the 2 points at which the surface intersects with these 2 axes, and let's connect them. Now this, as I said, since z is not involved, this plane must be parallel to the z-axis. So we draw a parallelogram that is parallel to z-axis. Right? So we have this. We have the plane that's described by xy plus y equals 2. All right, same story if say you have if you have a plane, if you have an equation that involves only one variable, for example x equals 2, then you know it is a plane that's parallel to the YZ plane. So you just draw a plane that is vertical to the x-axis. That's it. Okay, I'm not going to go through all of them here, but it shouldn't be too hard to figure it out. Next, we're going to study quadratic surfaces. Now, quadratic surfaces are surfaces described by a quadratic formula. So like this, the general equation for quadratic surfaces is ax squared plus by squared plus cz squared plus dx plus ey plus fz plus g equals 0. And a, b, c, d, e, f, g are all arbitrary constants. Now, quadratic surfaces, it's a little bit different than the surfaces we've learned so far. The other surfaces, we actually, the intuition is that we derive the equation from a shape that we're familiar with. Now, quadratic surfaces, this is the definition of quadratic surfaces. It is surfaces described by this quadratic formula. So it's not just one shape. In fact, with this general equation, there are 6 possibilities of what it looks like, and they're given here. So the general equation of quadratic surfaces describes these 6 shapes: elliptic cones and elliptic paraboloids, hyperbolic paraboloids, elliploids, hyperboloid of 1 sheet, and the hyperboloid of 2 sheets. Now, how do we know that? So, what I can do is let me show you, for example, how we know this equation looks like an elliptic cone. So the first thing to notice is that we can actually disregard the dx ey fz, because we can simply we can get rid of them by making this a complete square. So eventually, I mean, you're going to, for example, end up like a times x minus something. Say, let me use some other number. Say alpha squared plus b times y minus beta squared plus c times z minus gamma squared plus a constant, say h, equals 0. So for any quadratic surface given in this form, you can turn it into 3 complete squares and a constant at the end. Now, if you turn it into this form, then notice that essentially you're just moving this shape. Comparing to this, you're just moving this shape, alpha in the x direction, beta in the y direction, gamma in the z direction. So you're not changing the shape, you're just moving it. So it suffices to consider only the case where d and e and f are all 0. Is everyone okay? So that's the argument for considering only this, the second order terms. All right, now suppose we have an equation. Suppose we have the surface x squared divided by a squared plus y squared divided by b squared minus z squared divided by c squared equals 0. Now, before we actually wrote a times x squared, b times y squared, c times z squared. It's just when we were talking about elliptic cone, it's common practice to turn that into divided by a squared. It's just it makes more sense because you will realize that the cross section of the shape are actually either parabolas or ellipses. And when you're talking about ellipses, you usually write it in this form, right? So that's why we do this. Now let's consider this surface. How do we know that it is actually an elliptic cone? We do it by consider the traces of the surface. Okay, let's first look at the traces on any plane that is parallel to the xy plane. So the traces on any z equals constant, say m. Okay. All right. So if we let's look at this trace. Well, since it's on the plane z equals m, let's just plug that in there. We get x squared over a plus y squared over a squared y squared over b squared minus m squared over c squared equals 0. Let's add m squared over c squared on both sides. We get this thing equals m squared over c squared, right? Now this is a formula for an ellipse. When m is not 0. When m is 0, it's just 1 point x equals y equals 0. But when m is not 0, this is an ellipse. Now what does that mean? It means in the three-dimensional space, when we take a plane that is perpendicular not the best drawing. Let me start over. Would it be? Maybe it's better if we only draw half of the axes. Okay, so consider this this plane characterized by z equals m. All right, so this is m. What does it look like? It's something that looks like this. Okay, so it is a plane that's parallel to the xy plane, but lifted up by a distance of m. And the trace of this surface on this plane is an ellipse that looks like this. Okay, and we see as m decrease, it's not radius, but when we're talking about ellipse, we don't have a radius, but it's a similar idea, right? So when this number is smaller, it's not the radius being smaller; it's just the distance from any point on the circumference to the center becomes smaller. So what we have here is when m decreases, we get smaller and smaller ellipses, and when m becomes 0, we have a point. Okay, so we get stuff like this. Now let me get rid of the plane. When m is smaller, we get a smaller ellipse. Okay, so it's not a very good drawing, but you get the idea. You just get smaller and smaller ellipses when m decreases. Okay, so that gives you a cone shape. This is how we know it has a cone shape. Now, how do we know it is a cone instead of, say, a paraboloid, right? So if it's an elliptic paraboloid, you also get smaller and smaller ellipses on the cross sections. Well, we know it's a cone instead of a parabola because if we consider the trace on, say, the xz plane, we find that x squared divided by a squared minus z squared divided by c squared equals 0. Okay, and and we have x squared divided by a squared equals z squared divided by c squared. Multiply a squared on both sides and then take the square root. We get x equals plus minus square root of z squared times a squared divided by c squared, or plus minus square root of a squared divided by c squared times z. Okay, depending on if A or C is positive or negative. So this is the trace on the xz plane. So that means the trace on xz plane are two straight lines because it's x equals some number times z. That is the equation of a straight line. So that's how we know this is a cone. If you cut this, say perpendicular parallel to the xz plane, you get two straight lines that intersect at the origin. Same story, if you cut this perpendicular parallel to the YZ plane, you will again get two straight lines that intersect at the origin. And all these information combined give you an elliptic cone. I'm not going to do all six of them in detail, but I highly suggest you try these yourself. Just look at all the traces on XY plane, XZ plane, YZ plane, or traces on say these flat surfaces Z equals M. Look at what they try to write out these equations and see what they look like, and see if you can make sense of these shapes. For example, elliptic paraboloid. As I said, the only difference is that now if you look at the cross section on the xz plane, for example, if you take y to be 0 here, you get x equals x squared over a squared, which is a parabola, hence the name elliptic paraboloid. And if you get paraboloid traces on xz plane, yz plane, and ellipses on horizontal cross sections, then this is the shape you get. Okay, let's try to let's look at two practice problems. We want to classify these two surfaces. The first one is x squared minus 4y squared minus 4z squared minus 4 equals 0. Now, in general, classifying quadratic surfaces is a lot easier than drawing them. It takes quite a while to draw these shapes out on a piece of paper. As you can see, I didn't do a very good job. But classifying them is much easier because all you do is you look at how you can manipulate this equation into one of the 6 forms given here. Okay. Now, x squared minus 4y squared minus 4z squared minus 4 equals 0. Now, if you look at the general formula, the general equation of the 6 shapes in the picture in the previous page, you realize that we get rid of all the coefficients and put them on the denominator. So that's the first thing we will do, since the largest coefficient here is 4, so we divide the entire equation by 4 and get x squared over 4. Well, 4 is 2 squared, so let's write 2 squared minus y squared over 1, right? So 1 squared minus z squared over 1 squared. Minus 4 equals 0, so add 4 on both sides, we get equals plus 4. All right, so this is called, this process, maybe you can call it normalization. So we get rid of all the coefficients in the numerator and put them on the denominator. All right, if we scroll back and look at all these equations, we'll find that it is this one, a hyperboloid of 2 sheets. A hyperboloid of 2 sheets is characterized by an equation like this. You get two negative squares and one positive square, and that is a hyperboloid of 1 sheet. Oh, I made a mistake. When you divide 4, this becomes 1, right? Okay, so of course you can try to graph this yourself and look at all the traces and stuff, or you can just do what I did, just compare this to the 6 equations uh, given in the picture. All right, let's try another one. X squared 2x squared minus y squared plus 2z squared equals minus 4. Now, once again, we divide the entire equation by the largest coefficient, which is 4, negative 4 here, or 4. It's the same thing. So what we have here is if we divide everything by negative 4, we get x squared divided by negative 2, so minus x squared divided by 2 plus y squared divided by 4, then minus z squared divided by 2. And once again, this is a hyperboloid of 2 sheets. Honestly, I'm not sure how to spell hyperboloid. Huh. Alright, so this is how you classify quadratic surfaces. That is all for today. The web work assignments are already posted. Please, as I said, please try to draw the traces and classify the traces yourselves. That will really help you understand how these quadratic surfaces work. All right, and I will see you all either in office hour today or next week in lecture.